Look at your CFU for chapter 3.3 where we're focusing on our linear regression equation, finding the slope and y-intercept and interpreting those in context of the problem. So in number one it says, what's my line? So it says an eccentric professor believes that a child with an IQ of 100 should have a reading test score of 50 and that a reading score should increase by 1 point for every additional point of IQ. What is the equation of the professor's regression line for predicting, a score from IQ? So when we want to do this, first thing that I want to do is define what my variables are. So y hat, remember, in this unit we're going to use y hat, and that's going to represent a predicted y value. In this case, our predicted response. We're trying to predict reading scores. So right there, it's just simply the predicted reading test score. Now, for my x value, what am I using to predict the readings test score? I am going to use the IQ. So basically though, it's the number of IQ points, since he's saying for 1 point additional, we're starting at the 100. So it's going to be important that I note that, because when I come up with my equation, it's going to be actually starting a little bit different here. So we're going to say the number of points above 100 for a child's IQ. So we're going to assume it starts at 100. So when I get my equation here, since I'm starting and saying here that x starts at 100, we would say that they would get a score of 50 when at 100. Plus an additional point, so 1x for each additional point, or each additional IQ score. The reading score should go up by 1 point. That is my slope. All right, that takes care of number one. Number two, IQ and reading scores. Data on the IQ test scores and reading scores for a group of 5th grade children gave the following regression line. Predicted reading score equal -33.4 plus 0.882 times the IQ score. So sometimes instead of using the symbols, here's predicted reading score y hat, IQ score is x. So sometimes they'll actually use what they are instead of the symbols. So in this case, the first thing it says, interpret the slope, or what's the slope, and then interpret it in context. So the slope is the number in front of the x. So my slope equals 0.882. So what does that actually mean? Well, for every increase, 1 point increase in IQ scores, my predicted reading score is going to go up by 0.882 points. So we would say we predict that the reading score will go up by 0.882 points for each 1 point increase in IQ score. All right, next one. B says, what's the intercept? Basically, what's the y-intercept? So my y-intercept is equal to -33.4. Explain why the value of the intercept is not statistically meaningful. Well, what does this actually mean? It means an IQ score of 0 would predict a reading score of negative 33.4 points. Well, since reading scores should be 0 or positive, this predicted value doesn't make sense. Also, one could argue that, can someone actually exist and have an IQ of 0? Well, I suppose since it's a test, they could. So, hence why I went this route, talking about how you really wouldn't have negative reading scores. Alright, so now, it asks you in C to find the predicted reading score for two children with IQ scores of 90 and 130. So for the first one here, an IQ score of 90, all I'm doing here is plugging it in to my calculator into the equation. So I type in negative 33.4 plus 0.882 times 90. So if you enter that into your calculator, you get a reading score of 45.98. So I'm just going to note an IQ score of 90 has a predicted reading score of 45.98 points. I suppose if you rounded that to 46, it'd probably be okay. Do the same thing for the other one. It says to do it for 130, so an IQ of 130. Same process. Y hat equals negative 33.4 plus 0.882 times 130. So y hat, if I plug that into my calculator, ends up being 81.26. So an IQ score of 130 points, or 130, I'll just leave it like that, keep consistent with the other, has a predicted reading score of 81.26 points. Now it's very important that you are saying predicted, because your Y value is not just a reading score, it's a predicted reading score. There's a difference between the two. Alright, let's flip to the back side. Question number 3, how much gas? Here we examine the relationship between the average monthly temperature and the amount of natural gas consumed in Jones' Midwestern home. The figure below shows the original scatter plot with the least squared line added. The equation to the least squared line is 1,425 minus 19.87x. So here's the temperature. As the temperature is increasing, okay, the amount of gas consumed in cubic feet is decreasing. So how is it decreasing? Well, that's your slope. So here it says identify the slope, so it's kind of a repeat of the first problem. Our slope is the number in front of the x, 19.87. What does this mean? Well, the predicted amount of gas used in cubic feet, okay, and I apologize, our slope was negative 19.87, is going down by 19.87 cubic feet for each additional degree in temperature that goes up. Okay? So, I'm just going to rewrite that. We predict the amount of gas consumed in Jones' home decreases, by 19.87 cubic feet for every degree increase in temperature. So for each additional 1 degree increase in temperature, we predict that Joan's going to use 19.87 cubic feet less of gas. All right, so the next one says, identify the y-intercept of the line. So, come on here. So my sorry, it's a little frustrating. I'm actually hitting down here the color, and sometimes it's not registering. Just like to switch colors. So my y-intercept is the 1425. Okay, so what does this mean? Well, that's when x is 0. 0 is the temperature. So when the average temperature is 0 degrees Fahrenheit, okay, the predicted consumption for Joan's place or her home is 1,425 cubic feet of gas. Okay. So now it says explain why this is risky to use this value as a prediction. Well, if you go up to the graph, the data points that we actually have only run from, it looks like, about 15 degrees to about 50, not even that much since this is 30. So it actually, and it's counting by 5s there, so it actually only runs from about 27 degrees to about 57 degrees. So really we should only use this line to predict how much she uses between those values. So since 0 falls outside, we are doing what's called extrapolating. So we'll just note here that this is a form of extrapolation. Since 0 degrees Fahrenheit is outside of the spread of data, used to create our least squared regression equation. All right, C says use the regression equation now to predict the natural gas Joan will use in the month with an average of 30 degrees. So I'm just going to now take my equation, right, and plug in the values. So 1425 minus 19.87 times 30. So I'll plug that into my calculator and it's going to give me a predicted value of 828.9 cubic feet. Okay. So again, I'm just going to answer the question real quick. So when the average temperature is 30 degrees Fahrenheit, okay, when it's that, we predict that Joan's home will use 828.9 cubic feet of gas. All right, last one, D. Okay, says, would it be appropriate, okay, to use the regression line to predict Jones' natural gas consumption in a future month with an average temperature of 65 degrees Fahrenheit? Okay, justify your answer. So this is very much like in question B, is 65 within our spread? And in this case, it's not. So we would say no, since 65 degrees falls outside the spread of the given data used to find the least squared regression equation. Okay. Sorry, excuse me as I cough there. So again, since 65 degrees falls outside the spread of the given data used to find the least squared regression line, this is a form of extrapolation and would not give an accurate prediction. Now, technically, it might be able to give it, but when you go outside your data, you're risking that it's going to be off. All right, that ends your video.